Hey guys, sorry I'm not here today, but we're going to talk briefly, well, actually I hope it's briefly, about ideal gas law. And so let's go ahead and get started. Let me share my screen here. Oh, I totally messed up, sorry. Here it goes. Okay, so what we're going to talk about, ideal gas law, is the PUVNERT, or PV equals nRT. So the ideal gas law, we're going to treat all gases as though they're ideal, which is to say that they have no intermolecular forces. We're going to say that they're exactly the same size, and they don't interact with each other in any way, which is not really true, but we're going to go ahead and say it's true. And we'll use that for all of our gas laws. So anyway, if you combine Boyle, Charles, and Avogadro's laws together, you really get PV equals nRT. The R value that we're going to use most often is going to be 0.08206. That number is on your, I'm bringing it out. That number is on your formula chart. There is another one given as a gas constant. Actually, there are two more. One is for an energy calculation, which is the first one of the R values. We won't use that one for any of this. But the third one is 62.36 liters torr per mole K. You could use that instead if you were using torricellis instead of atmospheres for your conversions. But I would just stick with atmospheres. It's easier. We used 0.0821, I think, last year in pre-AP, but 0.08206 is what's on the AP chart. Anyway, but yeah, most gases behave ideally at pressures that are less than an atmosphere. But for our purposes, we're just going to say that they behave ideally no matter what. So here we're actually given the gas pressure inside an aerosol can is given at 1.5 atmospheres. The aerosol can itself isn't going to change volume. Cans aren't going to change volume. So the volume would be constant. So instead of using P1 V1 over T1 using a combined gas law like this right here, you would shorten it just to take off the volume. Had they given you the volume, like a lot of times they'll tell you that it's on a 1 liter flask, but the flask isn't going to change volume. Then you just use 1 liter on both sides of the equation or just get rid of the volume. But anyway, you would plug in your pressure and your temperature. Be careful. Temperature, you can't use 25 degrees C and 450 C. You'll have to change those to kelvins. You do that by adding 273 or 273.15. In this case, we just added 273. And you would do your division and solve and get your answer. This answer, of course, would be in atmospheres since it was atmospheres, unless they ask for a different unit of measure for pressure. Atmospheres is what we would do it in. I'm going to go kind of speedy because I'm kind of running out of time doing the video. So if you guys need time, just tell us to push pause and we'll push pause and let you guys catch up. In this second question, now we're just doing combined gas law problems here, but we'll do some PUVNERT here in a second, some ideal gas law in a second. But quantity of helium gas occupies a volume of 16.5 liters at 75 degrees C and 45.6 atmospheres. What is the volume at STP? You would just have to know what your STP values were here and plug them in as your second pressure and temperature. So 0 degrees C, add 273 would be 273. And your pressure would be 1 atmosphere, and you would just solve for that final volume. Another way to do this is to use PUVNERT, solve for the number of moles, and then multiply by 22.4. Either one would work. You might get a slightly different answer, but it would be okay. When you're doing these, I would do a Geoffroy method, given formula work answer. I would list the variables that you have for each one. I don't know how this is going to show up on here, but we'll see. I would say that that's terrible, that V1 is 16.5 liters, and I would list the others as well. So my T1 would be my 78 degrees C. Don't forget to add 273. And then for my initial pressure, it would be 45.6 atmospheres. And I would use those three as my P1, V1, and my T1. For your P2 and your T2, it's standard temperature and pressure. So my T2 is going to end up being 0 degrees C, which is 273 K. And then my final pressure would be 1 atmosphere. And then you would just solve for V2. So I'll show you the work. Didn't want to spend a lot of time on these, but you would just plug in, and I've got X in there for the variable. You would just solve for V2. And so Yeah, your V2 would end up being 585 liters. An easy question, but where students make mistakes is forgetting to add Kelvin. Forgetting to add 273 for the Kelvin conversions on your Celsius. So here's your ideal gas law. Really, all of the gas laws are really the same. They're all this. They're all the ideal gas law. The only thing is that when we're usually talking about changing a pressure, volume, or a temperature, and then what is its new pressure, volume, or temperature, we're saying that the number of moles is held constant. And so actually, if you set N equal to N, you end up with PV over T equals PV over T, and the R's would cancel on both sides. So all of these formulas are really the same thing. So it's really PUVnert. You're just, if you manipulate one of the variables and you get a new variable and it's the same number of moles of gas, you just set them equal to each other. So the combined gas law is just the number of moles equals number of moles, and you substitute in pressure, volume, and temperature. So we'll do a couple of these examples, and I'm just going to show you the work. I would like you to try them on your own. This one here says gases shipped in high pressure containers. If a steel tank whose volume is 50 liters contains oxygen with a total pressure of 1550 kilopascals at 23 degrees C, what's the mass of what mass of oxygen does it contain? We need to find mass. So in order to find mass, we're going to have to use a formula. We're not changing anything from one side to the equation to the other. So it's definitely going to be a PUVnert equation. And so you'll solve for the number of moles, and then you'll change the number of moles to grams using the molar mass of oxygen. Careful, oxygen is O2, so it'll need to be 32 instead of 16, but very straightforward problem. Go ahead and give that one a shot. Ask that you press pause and give them a second to do it. And then unpause when it's time, and I'll have the answer up there. So here's the work here. If you use PUVnert, go ahead and solve for the number of moles first. And then once you know the number of moles, don't do any rounding in between because you're not changing operations. Whatever that entire number is of the 30.47, plug that in times 32 and you get 980 grams to 2 sig figs. Yeah, that 2 sig figs is really, well, is it 2 sig figs here? This one is wrong. I would say this is wrong, guys. This says 1500, but up here it said 1550. We'll roll with the 1500 calculation, but you really should have used 1550. Probably get a little bit larger answer over there, something over 980. And it should be to 3 significant figures. This is a mistake on my part. My bad. Still moving on. So here, calcium hydride reacts with water to produce hydrogen gas. There's the formula it's given. Assuming complete reaction with water, how many grams of calcium hydride are required to fill a balloon to a total pressure of 1.12 atmospheres at 15 degrees C if the volume is 5.5? This is just a straight up PUVnert problem. You would be looking for grams again. So it will be done very similarly to the last one. So go ahead and give this one a shot. Remember your R value is 0.08206. And I'll come back with the answer. Hit pause and let them give it a shot. Okay, so here's the work. At the beginning, they're doing the PUVnert and solving for the number of moles. You get 0.261, and then take that and change it to the number of grams instead of calcium hydride, so the original amount to produce that hydrogen. So the data that they're giving you at the beginning for the pressure, volume, and temperature is for the gas. The gas that was produced was hydrogen. So that'll give you the moles of hydrogen. Then it's just a little bit of stoichiometry. 1 to 2 mole ratio from our balanced equation, multiply times the molar mass to get your answer. So on the next one, how many liters of nitrogen are required to produce 115 grams of ammonia at STP? Same thing, you'd have to write a balanced equation first. So it wants to know nitrogen would be necessary to produce NH3. So what you're going to add to that's going to be hydrogen. You'll need to balance the equation. And then it said standard temperature and pressure, and they're asking for volume. Volume at STP, you should know, is 22.4 or 22.42 liters. So this is just a straight up stoichiometry problem. So see if you can do this one. Do the pause thing again. You got to balance the equation and then use that balanced equation to solve for that problem. So there we are. There's the balanced equation, just nitrogen, 3 moles of hydrogen. It's a 3-to-2 ratio with the ammonia and a 3-to-1 ratio with the nitrogen, or 2-to-1 ratio from the ammonia to the nitrogen. So it says we're given 115 grams of ammonia. The molar mass is 1704. The conversion factor, like I said, is 1 mole of nitrogen to 2 moles of ammonia, and then use Avogadro's law, which is 22.4 liters is 1 mole of any gas at STP, and get your answer. You could use PubNert to solve this problem, actually, to tell you the truth. You could plug it into PubNert and solve using the standard temperature and standard pressure to solve for volume. You would get an answer that's kind of close. It won't be exactly the same, but if I saw you'd worked it that way, it would be okay too. So last thing that we're going to talk about is molecular weight and using density of a gas to solve for it. You can totally use PubNert to solve these problems, but it's a whole lot easier to use this equation. We introduced this in pre-AP, but if you want to find just the molecular weight of a gas, you can use the dirt over the P. And then we say that cats put their dirt on top of their P is a quick and easy way to remember this. But you do have to know that the density is going to be in units of grams. Oh, it's right there. In units of grams per liter. That's a little different than grams per mil, but you'd have to make sure it's in grams per liter since volume would be in liters, and it'll end up giving you the molecular weight. I could derive it for you, but it's really not necessary. You can certainly use PubNert to solve for this. And if you knew the amount of grams and you solve for the amount of moles in PubNert, you would just take your grams over your moles and you have your answer. It will work the same way. So here's a little example. Calculate the molecular weight of a gas. You have the mass. They're giving you the milliliters, change to liters, and they're giving you the millimeters of mercury, which you'd have to change to atmospheres. List your variables, plug them all in, and I would use the kitty cat or molecular weight kitty cat. Meow equals dRT over P. So go ahead, pause, give that one a shot, and I'll show you the stuff on the other side. So here it is here, dirt over P, solve for your density, change your temperature, of course, to kelvins. If you only had 273, it's totally fine. You're going to lose the 1.5 when you do your sig figs anyway. And then your pressure ends up being 0.507. In truth, you really shouldn't do any rounding until the end here. The 0.507, you should use the entire number that's there. You end up getting a molecular weight of 40.4. If they gave you a list, and this happens a lot, if they give you a list of compounds, you would need to find one of those compounds that has that molar mass to identify the compound. And that's what we actually do, or we will do in our lab next Thursday, which, by the way, we have another lab next Thursday. And that's it. So that's a short lesson. You guys have time in class to knock some stuff out. You have the lab to write up for next week as well. And I'll see you guys on Monday.